Record. Okay. A little bit of review. We started working with the normal distribution. We established a lot of facts about the normal distribution, but the main thing that we focused on was, okay, if I have something that follows a normal distribution with some mean mu and some standard deviation sigma, first thing I'm going to do to be able to find probabilities associated with this thing is I'm going to shrink it down. I'm going to standardize it to be on the Z curve. Okay. So how do we do that? We worked up towards, okay, fx is the observation that I'm interested in. All right, so I'll add that here. X is the observation I am interested in. Oh, and you weren't here last day, or if you forgot your table or your formula sheet, I have spares up at the front. You'll have to come grab them. Close this door. So X came from a distribution, a normal distribution with a mean mu and a standard deviation, so sigma. So that's where these mu and sigma came from. Okay, and so what are we going to do? We're going to standardize them onto a Z curve. Now, a couple of quick Z facts is it follows a normal distribution, right? So the shape, we know the shape. The center of Z is at 0, and the standard deviation of Z is 1. We also said that, okay, just as a rule, we'll only be able to move out 1, 2, 3 standard deviations from the mean in either direction before we kind of run out of space. But that's not really true though, right? Because here I go to -3, -2, -1, 1, 2, 3. But also remembering that these tails don't close until you hit infinity, which you'll never hit, right? And so they never close, right? So it goes out to positive infinity and negative infinity. So it is possible to be 50 standard deviations above the mean. It's just what? Highly unlikely, right? So it is possible, right? But it's very unlikely because how do we attach probabilities to the number of standard deviations I am from the mean, right? Because Z is the number of standard deviations from the mean. X is, right, negative if it's below the mean and positive if it's above the mean, right? But it's the number of standard deviations away that your observation that you're interested in is from the mean. Okay. So then what we said was, okay, the area under the curve is a probability. So it's the probability of these things happening. So the area under the curve is a probability. We know things about the probabilities. The main one that we keep going back to is that the total area under the curve then must be 1, right? The total probability of all the possible things from negative infinity to positive infinity must be 1. So therefore, the total area under the curve is 1. And we use that a lot, right? Because then what can we do? Well, if I tell you the area to the left is 0.3, then what's the area to the right? The probability of being greater than that thing must be 0.7, right? We know those from complements before, right? And so we use the complements quite a bit. In fact, we saw in Excel, it will only return the area to the left, and then you might, if you want the area to the right, you have to do a little bit of legwork, right? Subtracting that from 1, right? But knowing the total area is always 1 is going to be very useful. In fact, for finding areas under the curve, we use symmetry, right? We can start here. If Z is 0, then the area under the curve, let's say, to the left must be 0.5, and to the right must be 0.5. Right, splits it in half. Otherwise, it's not symmetric anymore. Right, so 1 divided by 2, half and half. Okay, and so then we said, okay, the area in one of the tails is 0.5. The area in both of the tails is 1, right, from 0. That's not usually what we're interested in, right? We're usually interested in kind of values out here, right? So then we're going to use a table. And that's the table that you have here. So if you don't have one, it might be nice to have it because we're going to work with it quite a bit today. And so if you still don't have one, come grab one. But I updated the table on Moodle, so it's just this table and not the big Z table. Yeah. So we're going to use this Z star line, right? That's our Z. Notice that they're all positive, but that's because by symmetry, the negative side behaves the same way, right? And so the one-sided P tells you the probability in the tail, in one tail. So the one-sided P is the probability in one tail. Talk about the tails. So we looked at an example where we let Z be 0.674, right? And so when you've calculated your Z, you're going to look here and be reminded that, okay, I've got 3 decimal places here, which means that I should have at least 3 decimal places in my answer so that I can place it properly. You don't want to round more than 3. Okay. Which is different because if you use the Z table, it's 2, but this way we're just using the one table throughout the course. Okay, fine, there's a little table later. It's different. Paper. So it's the probability in one of the tails. And so what's that going to look like if we draw 1.96, a Z of 1.96? Z is centered on 0. And if I move out to 1.960, I'm told that the area in one of the tails is 0.025. And then the two-sided P, we're not going to use a terrible amount because that's just the area in both the tails, or not a huge amount yet. We will later. Okay. But what does that tell us? That even at 1.960, negative 1.960, this area is also 0.025. So you double it. Rendering this second line pretty useless. You only need the one-sided P, the area in one of the tails. What does that mean? What's the probability of having something less than 1.96 standard deviations above the mean? Woof. Okay. This area here must be 1 minus 0.025, which is what, 0.975? Yeah. This isn't review anymore. But what if we wanted to find just this area? How could you do that? These are just puzzle pieces. You can subtract pieces just as long as you don't treat them like a rectangle, right? They're not a rectangle kind of width times height. It doesn't work that way, right? But we do know the areas, right? And so what if I wanted to find this area here in the middle? If I know the area, I can tell you got it. I know. It's good. So keen. I won't make you articulate it though. How about that? So brave. But I think we see it, right? Or maybe not yet. But we have this piece, right? So this whole, I'll temporarily shade it, right? That whole area is 0.975. Obviously, I've gone above. But then if I lob off this area, which I also happen to know now, right? I'm left with the area that I want. And so I'm gonna remove that. But this area, the probability, which is an area, right? But the areas are probabilities. You need to make that link, right? If I'm trying to find a probability, I'm trying to find an area. Okay. So the probability of an observation being between plus minus 1.96 standard deviations from the mean must be, oops, undo, must be 0.975 minus 0.025. So 95% of the curve is within negative 1.96 and positive 1.96. How about just as a quick rule of thumb, we don't say 1.96, let's just use 2, right? But I think we can all be convinced, okay, 1.96 is basically 2, right? And so here, this is roughly plus minus 2. And that's how we got to that rule of thumb that said, okay, any observation that's more than 2 standard deviations away from the mean is considered unusual, right? And so it's because 95% of the curve is within these 2 bounds, right? So then if you're out here, the probability of being out in these tails is 2.5%. It's pretty small. Right, and so that's why we say, okay, just as a guideline, if you're more than 2 standard deviations away, those observations are considered unusual. So which is why any observation beyond plus minus 2 standard deviations from the mean, which is really just a z of plus minus 2, is considered unusual. right? We've covered most of our outcomes within 2 standard deviations. So that part is not reviewed, but it is kind of building on just using those areas in the table. Okay, then, well, any questions before I keep going?
This was a question, how would the numbers like, how would we take like, okay, this is what the question says, and then we put it into that, like, what's this kind of example of that? What would it ask?
So then I think I have an example coming up.
I don't know if that made sense, but
It did. But I'm saving it. Right, so it would be what's the probability of a measurement being between here and here? And then you would find that area. But we're building up to that.
that makes sense.
Nice and steady. Here, now we're ready. I said try it on your own and then pick up here on Thursday. Well, I did a little bit more, but and here we are on Thursday, ready to go. So these questions, the normal distribution questions, I have to give you the mean and the standard deviation of all the observations, right? And so, and I usually have to mention that they're normally distributed somewhere in the question, right? And so the reason I highlight that now is because on the test, you're gonna have to read a question and figure out, okay, what type of question is this? And so a lot of it is just identifying what type of question you have, and then that'll point you in the right direction on your formula sheet, right? And so what are some clues here? Well, let's read it. You've already tried it on your own, aced it already, I know. But here we go. At Heinz Ketchup Factory, the amounts which go into bottles of ketchup are supposed to be normally distributed. Okay, so I'm gonna react to that. Okay, that's good. With a mean of 36 and a standard deviation of 0.11 ounces, but who cares? I know, hopefully no chemistry or biology teacher walks by. Who cares about units? I certainly don't. Once every 30 minutes, a bottle is selected from the production line and its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, then the bottle fails the quality control inspection. Then we're asked what percent of bottles have less than 35.8 ounces of ketchup. So this first part, these highlighted sections, are the reason it's a normal distribution type of question. Okay? And so what that should do is it should guide you to say, okay, now I'm here on my formula sheet, and let me just bring it in. Right, so these things tell me that I'm here on my formula sheet. X then is the weight of a bottle of ketchup. So we're given some information, but we can take this normally distributed with the mean and the standard deviation, and we can draw this out, right? We can draw this distribution, or at least sketch it out. Now, you don't have to, but I really encourage you to, because it's worth part marks if you do just kind of sketch out the scenario. You can get full marks without sketching it out, but if you're looking for part marks, then sketching it out is definitely the way to go. Even if you sketch out the wrong thing, right? Showing me that you've misinterpreted the question, but then you followed through with that wrong thing and you solved it how you said you were going to solve it properly. That's worth a lot more than just kind of flip-flopping throughout the question. And so I encourage you to sketch it out. I will always sketch it out. But that takes practice, right? And so I've got, okay, first thing, normally distributed, I've got the shape centered on 36. And the standard deviation is 0.11, which I just jot down underneath. I don't spend very much time drawing out, so going minus 0.11, minus 0.11, minus 0.11. You could if you wanted to, but that's kind of too much. Some parameters that were given is that if it's below 35.8 ounces or above 36.2 ounces, then it fails the quality control. You're underfilling or you're overfilling, which shouldn't really be a concern, but then you're losing money if you're overfilling constantly, right? And so that's bad. So here, now for these drawings, I'm not going to spend a ton of time figuring out where 35.8 should go because I'm just trying to visualize it, right? And so I'm just going to put it here at 35.8. And then 36.2 I'll put up here. So we're told that any bottle that falls below 35.8, right? So that's this area here, or above 36.2, those fail the quality control inspection. Now we're starting small. And we just want to know what % of bottles have less than 35.8 ounces of ketchup. So 35.8, that's the value that I'm interested in. That's going to be my X, right? I want to find a probability or a percentage or a proportion. Those are all the same thing, right? Associated with 35.8. Now 35.8 is one of these cutoffs. And so really what I want to find, if I want to find a percentage or a probability, that's an area under the curve, right? And so what am I going to do? I'm going to find this area here for this particular question. Okay. What do I have to do? To find areas under the curve, I have to use the table. But in order to use the table, I need to have a z-score, right? So remembering that it goes X, you have to turn it into a Z to get it to a probability. You turn X into a Z using the formula sheet. Z is X minus mu over sigma. And then you can use the table with the Z to find the probability. Right? Later, we're going to reverse this process and work backwards. But for now, it's a two-step process. So from the formula sheet, right, you have that Z is X minus mu over sigma. The hardest part, I think, in the beginning is identify which one is the X, right? What thing is it that I'm interested in, right? I think it's going to be one of those things where when I say it in class, makes total sense, right? Well, obviously it's the 35.8, but then you sit down and you read your own questions and it's not so obvious anymore, right? It's going to take practice. But the thing that I want to find a probability associated with is the X. Okay, so I have to standardize this X. Standardizing means calculating Z. And I have 35.8 minus 36 divided by 0.11. Now I need a calculator. Divide by 0.11. I get a negative 1.818. Well, 18 repeating. I'm going to round that, remembering to keep at least 3 decimal places, right? So you can use the table. Negative 1.8182, just in case. Okay. Page. Okay. Now, this is negative, which makes sense, right? 35.8 is below the mean, right? So now what this looks like is we have this exact same curve. It's the same shape, but now Z is centered on 0 with a standard deviation of 1. And we found a Z of negative 1.8182. That's the same curve that we had here. It doesn't matter. It's just been shrunk down, standardized, right? But the area that we want is the same. Okay. Where are we going to find this thing? This is where we have to learn some tedious notation, but we're going to use the same notation throughout the course. And so this is the first time that we're, first time I'm hearing this. First time we're seeing it. So it's going to be a little bit clunky maybe, but what we're going to say is I'm going to use the same format always. Okay. And so I'm going to start with since, just because in math we always since this. And then what I'm going to do is I'm going to put my Z in absolute values in the center. Okay. Since Z, the absolute value of Z equal to negative 1.8182 is between 2 values. Okay. The absolute value, remember, it just drops the negative, right? Turns it positive. It doesn't just drop the negative, but it's a function that makes it positive. And why did I do that? Because if we remember the table only has the positive values, right? But that's okay, it's symmetric, so it works still. Okay. But then what I want is I want a copy of this little guy. Copy. And how about I put it up above here? Sorry. Erase that. Erase that. Okay. Because now what am I going to do? Saw it, but just once. And we didn't really line it up this way properly. I'm going to drop the negative, right? That's what the absolute value does. And then it's going to be between 2 values. Now, I have always had a hard time with inequalities, right? Until it's pretty funny because a student told me, oh, well, you know, you just turn your, whatever makes an L, and then you can just read it as less than. I didn't know that. So that's useful. That's good to know. But then what are you going to do? So Z, our Z that we've calculated is going to be between 2 values here, right? remembering that Z is just increasing as you move out. And so here, 1.8182 is going to be somewhere between these two values. All right. So then what I'm going to do is I'm going to jot those down, 1.645 and 1.960. Why are you going to do this step? Because if you just kind of you're hurrying and you're you're stressing out, and for some reason if you tell me that 1.8182 is somewhere between these two values, but then you followed through with that, that's fine. That's okay. That's like half a mark off. It's no big deal. Okay. And so, right. So that's why you want to always kind of show me what you're thinking so that I can follow it, and then I can give you the most marks possible. Because although we're here for fun, I know it's also about grades. So your job to show me all your thinking so you can have the highest grade possible. Okay, so what does this look like? Negatives are weird, but means that Z is somewhere between negative 1.645 and negative 1.96. Read those backwards, right? But this looks like this. So I might have negative 1.645 and somewhere between negative 1.960. I want this green area. Oops. Oh, come on. Right. But the best we can do with the table is just give a range, right? And so now, so how we're going to read this is that since Z is between 1.645 and 1.96, if I drop the negative, right? We know, oops, combining those words, we know, you don't even need the we know, but then the probability, the one-sided P, and I do it like this because I don't want to have to think about the inequalities, right? Just list your smallest one to your biggest one. And I encourage you to do the same because it trips me up if you use opposite signs and I really have to think about it. As long as what you're saying is technically true, then that's fine. But I use the same inequalities, right, as before. And notice how I put the one-sided P is between two values, right? And so that's where it's helpful to draw it out like this, right? Remembering that negatives are increasing as you move to the left instead of the right, of course, but that doesn't matter. Well, it does actually, but the area in the tail associated with 1.645 is 0.05. And the area in the tail associated with 1.96 is 0.025. Which means that my one-sided P is somewhere between 0.025 and 0.05. Yeah. So it's somewhere between the smaller one and the larger one, of course, but that's where you want to be careful and read it from right to left, because as you're moving away from Z equals 0, right, what's happening to the area in the tail? It's getting smaller and smaller and smaller and smaller, right? So as your Zs are increasing here, the areas in the tail get smaller and smaller and smaller. So then to read them properly, you have to read them from right to left. Okay. Or draw them out like this and it'll be obvious, right? You would list them from 0.025 and 0.05. Okay. Good. So then therefore, the probability, sorry, we want a percent, but we can just multiply by 100 to turn these into percentages, right? Therefore, what percent of bottles have less than 35.8 ounces of ketchup? Therefore, between 2.5% and 5% of bottles have less than 35.8 ounces of ketchup. If we wanted the exact probability, right, we know it's somewhere between 2.5% and 5%. So that gives us a pretty good idea of where it is, but we can use Excel. I think I have a different sheet open here. How do I'll just open one, open a new tab. Do you remember? Equals norm dot, and then it gives me all the options. It's going to be norm.s.dist. Now, I don't really remember all the commands. That's not what this is about, right? You can always Google your way to it, right? Or if you have a jumping off point, right? Oh, it's a normal distribution. Maybe it starts with norm. Oh yeah, that sounds familiar. And then just kind of talk yourself through them and say, okay, well, because we're just going to use the norm.s.dist because it's a sample. Z was, I can do the negative 1.8182. And then cumulative is true because I want the area up to and including that point, not just at that point, which would be 0. So then true, oops. And then it did something weird with the brackets. That's okay. There we go. And that is the area to the left, right? Because Excel only gives me the area to the left, and I wanted the area to the left of a negative number, so it is the area that I want. Is this between 2.5% and 5%? I think so. So that's good. So now I'm going to screenshot this so we can see. Oi, that's loud. Crop. Or using Excel, we find the probability is 0.034517 or 3.4517%. Just making sure that it falls between those values that you set. And I want to highlight that I am showing the command that I used there. Okay. Good. On the test though, right? This is the answer, right? You're not going to have Excel on the test. But it's nice to be able to check your work. Nice. That's the percentage that's underweight, right? And I'm guessing I have a follow-up. And these options are no longer available to us. What percent of bottles pass the quality control inspection? Okay. So now I have a different question, right? We already drew out the scenario of where they pass and where they don't. So I'm going to copy this. Oh, actually, because I want to delete this. Orange. The orange highlights are the ones that do not pass inspection, right? And so let's use pink for the ones that pass the quality control. That would be all the area between these two values, right? Okay. We already know what this area is, right? 35.8 from earlier, right? And so we said, okay, it's somewhere between here and here, 0.025 and 0.05. So we had a range. This is where this method is a little bit trickier than using the Z table, where it just gives you probabilities associated with a Z. But like I said, it will be worth the work later. Okay. So we did this side already. How about we do the other side? Do you already know what it is? We know, but let's do the work. How do we know? Because this one was 0.2 below and this one's 0.2 above. So it should be the same, but let's do the work anyways. So we have already found the area in the tail for 35.8 ounces. So now we do the same for 36.2 ounces. Found a range, but that's okay. For 36.2, we didn't talk about how we would find this area, but, and there's a lot of ways, right? These are just puzzle pieces that we're working with, right? So whether you want to use the total area being 1 and then lob off the tails that you don't want, then you're left with the middle that you do want. That's how I'm going to do it, because we already did the work of finding one of the tails. So I can already lob off one of the tails from one, and then I just need to find the area in the other tail and I can lob that off. And then I'm left with the area that I want. There's lots of ways that you could put together these puzzle pieces, right? A weird but legitimate way that you could do it is you could say, okay, this splits it in half, so I have 0.5. And then what could you do? You could still take away this area. Kind of weird. Better would be, okay, if I find the area to the left of this little guy, right? And then I take away the area over here, right? Then I'm left with this piece that I have, and then I take away the piece that I don't want, I cut it off, right? So there's lots of ways that we can go about solving it. I'm going to, I'll use the method where I just take both the tails off of one, right? Take it away from one. But think about how you would kind of naturally get there, right? What your brain process is, and then just follow through with that. As long as we get the same answer, you're good, right? And so better than to learn a different method that doesn't really make sense to you. If you have a way that you can see, it's obvious to you how to find this area, then just use that method. Because like I said, there's a lot of different ways. But I am going to find the area in the tail of 36.2. Now the tail is now on the upper end, right, of 36.2 because I'm on the right-hand side of the mean. So what's the first thing I need to do? I need to standardize this thing. Z is x minus mu over sigma. And I'm going to need another page or two. Start with one. The thing I'm interested in is the x, 36.2. So I get 36.2 minus the mean, which is 36 divided by 0.11. 36.2 minus 36 divided by 0.11. Surprise, surprise. 1.81818, repeating. So Z is roughly 1.8182 again, but positive, which makes sense. We moved the same distance away from the mean on either side, right? Which is not always going to be the case, of course. So now I can sketch the standardized curve out if you'd like. 1.8182. From the table, do I have it? No. Thought maybe I had it copied already from earlier. It's the same scenario, right? If I take the absolute value of 1.8182, it becomes 1.8182, and 1.8182 is still between 1.645 and 1.96, right? And so those areas are the same. But now in the positive direction, 1.645 and 1.960. 0.025 and 0.05. Let's write it out how I want to see it. Since, and then next line, the absolute value of Z equal to 1.8182 is between two values, is between 1.645 and 1.960. We know the one-sided P is between two values, and we read those from right to left, right? Makes it easier if you've sketched it out, but you don't have to. 0.025 and 0.05. Again. Okay. We want, no, I'm gonna copy it actually. Otherwise it's too much drawing going on. Copy. I'll remove this. So by symmetry, because they're the same distance away, we found that it's somewhere between 0.05 and 0.025. We can still use that to find that pink area that we want. It's again just going to be a between two probabilities, right? And so, or percentages if you convert them. What's the smallest area between this 0.05 and 0.05, right? Is going to be the smallest possible size for this question mark area. Oops. Up to the largest size, which is where we take away 0.025 and 0.025. And maybe I'll remove this question mark and give myself a little bit more space. So this area is 1 minus 0.05 minus 0.05, which is 0.90. Wait, it's hitting 0. All right. Out to the largest possible area, which is 1 minus 0.025 minus 0.025, which is 0.95. Which means that, did it want the percentage or the probability? Let's see here. Percentage. What percent of bottles pass quality control? Well, I know which one I can pick because only one of these is between the ranges, but I don't expect you to have that exact value unless you use Excel. It'll tell you. So therefore, between 90% and 95%, oops, of bottles pass quality control. There's one more link that I don't expect you to see, but that we will kind of look at because we've moved the same distance in either direction. This is linked to the 90 and the 95%, right? It's between 90 and 95%. I only want to mention that. I don't want to bog you down with that, but there is a link there with this top row, which I have said we're going to use, but we haven't used it yet, but we could. Okay. How about in Excel? How are you going to do it in Excel? Let's see here. So I have the area in one of the tails, and I know by symmetry the other tail has to be the same, right? And so, oops. Let's see if I can. I always say, oh, I'm going to change the settings there, and then I never do. Because as soon as I'm out of the Zoom room, I forget. But in Excel, one of the ways that you could do this is you could say, okay, this is going to be equal to, where's my equal sign? There. Equals 1 minus, I'll use brackets, 2 times this little guy, 2 times A1. Close the bracket. Return. That'll wake you up. You can play around with other ways that you could find that probability, but that's probably how I would do it. Again, this is for this calculation here, or using Excel, 93.0966% of bottles pass quality control. But is 93.0966 between 90 and 95? Sure is. So, yeah. Nice. Any questions about that one? So mapping out the areas is going to be super useful, but it is going to take time and practice, right? Kind of practicing drawing those out. Finding cutoff points. So now we've got a different scenario, right? Body temperatures of healthy humans are distributed nearly normally. Hey, okay, I'm going to react to that with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. What is the cutoff for the lowest? And I'm going to change it to 2%, just so it is a value that we have on the table, and I'll make sure that it is, of human body temperatures. So finding cutoff points is going to be the backwards. I said it would happen, just didn't think it would happen so soon. Right? So we've been working from a cutoff point, going through a Z to find the probability. But now I have a probability and I want to convert it to a Z and then find X, which is the cutoff. So here, now I'm moving in this direction. X is the cutoff, which means I have to be given a probability or an area under the curve. And then I can move the other direction. Now, how we get from a probability to a Z is the same way that we moved from a Z to a probability. We use the table. And how we get from a Z to an X is the same way we got from an X to a Z, which is Z equals X minus mu over sigma. But now you have to solve for X instead of Z. So now we just do it in reverse, okay? Working backwards. So seeing these three things, right? Nearly normal or something normally distributed with a mean and a standard deviation, that sets you on the right path to say, okay, this is a Z-score type question, we'll call it, right? And so now, first thing I'm gonna do is I'm gonna map this out. Ooh, pretty good. I've got the shape, the center, it's lagging. 98.2. And the standard deviation, I just jot down somewhere. Sigma is 0.73. Okay. This is where we need to be a little bit careful because this here is a temperature number line, right? And so with temperatures, right, then low temperature are the lower temperatures. Things like what's the winning time of a race? If you're thinking about things like that, the winning time is the lowest time if it's a race, putting you in the bottom. And so you just want to be really kind of aware of what this number line represents, right? So in this case, it represents temperature. And the lowest, I changed it to 2%. The lowest 2%, remember, it's just to visualize. I'm going to force this lower area to be 2%. I'm going to force it to be 0.02. Or maybe I should draw the line again. So now, right, this is the opposite direction. I'm forcing that to be 0.02, and I'm working towards finding what that value is, right? What's the cutoff for the lowest 2% of body temperatures? Okay. That means that I need to, looking at my kind of pendulum here, I have an area under the curve. I'm going to use the table to turn that into a Z. Okay, let's grab the table here. Is it in there? No, still no. How? Copy. And I'm gonna remove this stuff. Add a page. This is the area in one of the tails. So my one-sided P must be 0.02, which the reason I changed it is because I wanted to have a value that's on here. So I'm going to make sure that it is one of these values, right? 3% is not on here. I go from 5% to 2.5% to 2%, and 3 is not on here. So that's why I had to change it to 2, but that's okay. Careful that you don't use 0.2, right? Happens. But from the table, let's add a page. Oh, I already did. Nice. Look at me go. So here, from the table, we see the Z associated with a one-sided P of 0.02 is Z is equal to 2.054. So now I have a Z, and this is what I would expect to see you write on a test, right? Is just kind of the shorthand for that is more complicated than it needs to be, and so that's why I'm skipping it. So I just write it out in words, but I do want to hear where you got this 2.054 from. This is another case where if for some reason you accidentally use 0.2, as long as you tell me that from the table we see that the Z associated with the one-sided P of 0.2 is 0.841, and then you followed through with that, that's just a minor slip up. That's not a big deal to me, right? As long as you follow through, then half a mark off for those minor slip ups, but nothing crazy, okay? So it's not game over. It's not over till it's over. Okay, so now in our little kind of pendulum here, we've gone from a probability. We use the table to find the Z. Now I have the Z, and I can use the formula to solve for X. Well, and I'll use a different color. Now we can solve for X. Z is X minus mu over sigma. Z is 2.054, which is X minus mu, which was 98.2. I lost it, 0.73. Yeah. Divided by 0.73. I just use the same formula, but on your formula sheet it's already been rearranged, right? X is, and what order does it do it? Mu plus Z sigma. Whereas in my calculation, I'm going to have Z times sigma and then plus mu, but it's okay. So this becomes 2.054 times 0.73. Scooch. I want to stack my equal signs. It's X minus 98.2, which means X is, where is it? 2.054 times 0.73 is 1.49942 plus 98.2. I did two moves in that one line, right? I simplified this, I multiplied these together, I guess 3 moves, and then I added 98.2 over, but then I also put the X on the left-hand side because I want to have what I'm solving for on the left. It's a personal hang up. So then this goes on the right-hand side. But the equal sign, if A is equal to B, then B is equal to A. But if you're looking back at it later and going, what did she do there? That's what I did. What did I do wrong? I did something wrong. Don't worry, I know what it is. I can tell. Got it. 99.7, let's call it, is above the mean, which is, well, that's fair. But that doesn't make sense because that's not what I want. So what do I have to do? I should have used a negative Z, right? Gave me a positive. I'll do it in red because I didn't catch it soon enough. But we want Z equal to negative 2.054 on the lower end. Whew. Negative. Then I think I'm off to the races. Negative. Now I'll try it. I'll do it properly. Negative 2.054 times 0.73 plus 98.2. $96.70058, which makes more sense because the mean is 98.2 and I want to be below the mean, of course, for the lowest 2% of temperatures. So it's always good to check to make sure if your numbers make sense. You can catch mistakes like that one. I wish I could say that that was canned, but it wasn't. It was an honest mistake. So it can happen to anyone. Especially me. Okay. If we used the formula on your formula sheet, I'll just run through it so that you can see it. Uh-oh. X is 98.2 plus negative 2.054. Pretend it didn't happen times 0.73. But you'll get the same answer. 96.70058. It's just depending on how comfortable you are rearranging the formula, right? But nothing crazy. Therefore, the lowest 2% of temperatures are below 96.70058 degrees Fahrenheit. Good.
Sorry, this might be a silly question, but I was just wondering how you got that formula, like, you go off of it, X equals.
This one?
Yeah, like how you
Oh.
arranged it. I got a little confused because I forgot my formula sheet at home.
Oh, here. I have a formula sheet.
Thank you, sorry.
It's just
Oh,
been
it's right
rearranged.
there. That makes
Rearranged
sense. I
on
was
your
like, where did that
formula
come from?
sheet.
Okay, that makes sense.
Yeah. Just secret derivations. I'll sneak it on here just for completeness. Okay. Any other questions about that one? Okay. We'll do this one. It's the same. It's got a little, not a typo, but an error, I guess. It's the same distribution, right? Nearly normally distributed temperatures. This one will pick up the pace a little bit, right? Because we already saw one just like it. So let's draw it out. Centered on 98.2 and sigma's 0.73. And again, same clues as before. When I tell you the shape, the center, and the spread, it's a Z-score type question. What's the cutoff for the highest 10% of temperatures? The highest 10%. I'm gonna force this area to be 0.1. And this is where I should have checked in and said, oh, okay, is it gonna be positive or negative? But in this case, it's positive, so I'm kind of off the hook here when I use the table. But using the table, we find the Z associated with a one-sided P of 0.10. I guess we'll need it. Where is it? Copy. Put it here. Careful with your zeros, right? You don't want to be using 0.01 when you actually want 0.1. But here it is, 1.282. Is Z equal to 1.282? Double check that it should be positive. It is. Good. So then, which formula should we use? I'll use the first one, x minus mu over sigma. 1.282 is x minus mu, which is 98.2 divided by 0.73. But instead of showing all the steps, because I want to keep it on this one slide to show kind of the smallest amount of work that you could do. 1.282 times 0.73 plus 98.2 puts me at I did something wrong because I got 191 degrees, and that is probably bad. 1.282 times 0.73, maybe that's the problem, plus 98.2. That makes more sense. 99.13586. Rounding to one decimal place, we get 99.1.
Use the other formula to find that. Is that completely fine? Or
Oh yeah, as long as you get to the same place.
Okay.
Yeah. I'll do it in a different color because X is, I can never remember, is it Z mu plus Z sigma or Z sigma time or plus mu? They're the same, I just don't want to confuse anyone. 0.2, 1.282 times 0.73 should get 99.13586 regardless. Making sure, so a common mistake, I think, because people get kind of flustered in a test and you're trying to work through these quickly, but you have to multiply these two together first, right? And then add them to the 98.2, right? Bed mass, brackets, exponents, division, multiplication, addition, subtraction. Or I guess in the States they use PEMDAS, parentheses. Weird. We don't do that. It's the same though. Okay. Nice. Oh, any questions before we talk about the empirical rule? Which we're going to call just the 68, 95, 99.7 rule. Because it's more telling. What we could do instead of the table, we could just use the 68, 95, 99.7 rule. Yeah. How so? Well, we already saw that about 95% of the curve, the central 95% of the curve, falls within 2 standard deviations of the mean. We saw that it should actually be 1.96, but then we talked ourselves into, okay, that's basically 2. Okay. And so we could do the same thing for 1 standard deviation and 3 standard deviations. And so within 1 standard deviation of the mean, we have the central 68% of the curve. Then if we move out another standard deviation, so now we're out 2 plus minus 2 standard deviations, we have about 95%. And then 3, we have about 99.7% of the curve. Right? Knowing these areas, right, we can do extra things. This behaves like the table, right? Because if I know that my mean is here, like that, then I know I have 0.5 this way, and I have 0.5 this way. What if you had to find the area in this tail? So this goes to that point and this point. If I've got the central 99.7 or 0.997, then I have 1 minus 0.997 left over, but I have to divide that evenly amongst the tails, right? And so this area here is going to be 1 minus 0.997 divided by 2. It's going to be very, very small. 1 minus 0.997 divided by 2 is 0.0015. Or 0.15%, right? Very, very small. It's still a probability, it's just very small. And then by symmetry, we have also found that this area must be 0.0015. Scientific notation. Okay. So these cutoffs, I would argue, are probably a little bit more or simpler to use than the table. The table just has more cutoffs, right? At less logical intervals, I think. But we can use the 68, 95, 99.7 rule to figure out approximate probabilities. And I think I have an assignment question that kind of makes you work with the 68, 95, 99.7 rule. But just remember, it behaves the same way as the tables, right? It's just kind of rough approximations. Okay. I do want to highlight that it is possible for observations to fall 4 or 5 or more. I keep an assignment question on there where you're 12 standard deviations away from the mean and everyone freaks out. Well, how am I supposed to deal with that? Well, you can do it. It's just the probability of that happening, if it's positive, is less than 0.0015, right? Somewhere between 0 and 0.0015, for example. So the 68, 95, 99.7 rule is just kind of a quick approximation of the probabilities or the areas. So if you don't have a table, then these are the values that I would use, 1, 2, 3, right? Because what's the area? Let's say you find Z is, as an example, Z is 1.7. What's the probability in the tail? Well, first, a Z of 1.7 means I'm 1.7 standard deviations above the mean just because it's positive, right? And so that means that I'm at mu plus sigma, so somewhere between mu plus sigma and mu plus 2 sigma, right? Somewhere maybe here at mu plus 1.7 sigma. Because that's what the Z score is. Right? I can do the same thing as we were doing before. I can find this tail and this tail, and then my probability is somewhere between those two. How do I find each of those tail areas? Let's start with this top one here. This has to be, okay, so it's only the central 68%, right? So 1 minus 0.68, and then I have to split that evenly amongst the tails because it has to be symmetric still. So this must be 1 minus 0.68 divided by 2, which 1 minus 0.68 divided by 2 is 0.16. I can do the same with the smaller area with a Z of 2, or just mu up 2 sigma. But now from 2 sigma, by the rule, I have 0.95 in the center. So now I have 1 minus 0.95 divided by 2, which is 0.025. Oops, that's not very clear, is it? That's a huge range, right? The probability, the one-sided P is somewhere between 0.025 and 0.16. I wouldn't be very happy with that approximation if I was your boss. Oh, I don't know, somewhere between 2.5% and 16%. Could you do a little bit better? Maybe narrow that down a little bit. Even without software, right? That's why we use the table. But it works the same way as the table, right? Or we would use Excel to find what it is. Okay. So, but just using the 68, 95, 99.7 rule, we do get an approximation. It's just not very useful, right? What would it be if we used Excel? Mostly because I'm curious. I'll start one down here. Equals norm dot, or maybe should we graduate? Norm dot s dot dist gives me the area to the left, right? But I already know I want the area to the right. So I'm going to go 1 minus norm dot s dot dist of 1.7 comma true, because we're always going to use true. Hey, keeps adding. No. No. It keeps adding brackets, but I don't want them. There. That's a more reasonable. I'll show what I did in my screenshot. Oops. Hey. Oh. It's not misbehaving. I'm misbehaving. I did it weird. crap. Obviously, in a workplace environment, you wouldn't be giving such a large range. You would just find the area, right? But if you're ever stuck without a table, can you imagine that? No table, it happens. Then at least you have some range, right? 0.044565 is somewhere between 0.025 and 0.16 because it's quite easy to be between 0.025 and 0.16. But so you can use this kind of rough approximation. There was one year where I got crazy, or I think it was a couple of years actually, where I didn't use the tables. I only used the 68, 95, 99.7 rule. Oh, wouldn't that be nice? And software, obviously. So of course you can translate the 68, 95, 99.7. There's a typo here. $99.7%. No. Right. If you have the mean of 1500 and a standard deviation of 300, assuming it's normally distributed, then the 68, 95, 99.7 rule applies. So then what you could do is you could start from mu, 1500, subtract 300, one standard deviation, subtract another 300, subtract another 300, add 300, add 300, add 300. And then you could have cutoff points that you could look at, right? She loves doing these false ones. I don't like them, but we'll do them. So the reason, so I want to talk about why some of these, well, why they're true, except for the false one, because it gives us a kind of good understanding of z-scores in general. So the majority of z-scores in a right-skewed distribution are negative. Now z-scores, you can calculate z-scores for any distribution. The probabilities from the table will only work for z's coming from a normal distribution, okay? And so we can standardize any distribution. But what does a right-skewed distribution look like? That's been a while. But it has a tail to the right. Meaning, now we have to dig deep. The mean is always pulled in the direction of the tail, right? So here, the mean is being pulled in the direction of the tail. But these guys are all below the mean then. And that's the majority of the curve, right? And so these would be negative z-scores, and these guys would be positive z-scores, right? If you're above the mean or below the mean, that's indicated by a positive or a negative in your z-score. So here you would have negative z, and here you would have positive z. Making this true. The majority of z-scores in a right-skewed distribution are negative. That's true. Right. A lot of knowledge went into answering that, right? And so that's not obvious first time you look at it, maybe, but you are expected to know all those components, right? That's why it's such a snazzy question. In skewed distributions, the z-score of the mean might be different than 0. How could that be? Remembering that z is x minus mu over sigma, that's always the case. Even if the mean is pulled out towards the tail, if we're talking about the z-score of the mean, right? then this is going to be the same thing as Z is mu minus mu over sigma. Mu minus mu is 0. So the Z score of the mean is always 0. That's just how Z's work. So that's false. But let's work through the other ones, just in case. For C, for a normal distribution, the interquartile range is less than 2 standard deviations. So moving out plus minus 2 standard deviations. Let's start with a normal distribution because that's what we're told. So that's going to be symmetric at the mean. But if it's symmetric, then the mean is also the median, right? Again, a lot of chapter 1, chapter 2 knowledge going into answering these questions. Okay, so if the mean is the median, which is what we link with the interquartile range, right? The interquartile range is the central 50% of the data around the median, right? And so, and if it's symmetric, then the interquartile range, I'm going to draw here, is the central 50%, right? From Q3 to Q2, from the median, right? The interquartile range is Q3 minus Q1. Split these into quarters. The area under the curve gets split into quarters, right? Which means that this little guy here might be Q1. And then this little guy here is Q3. The median is Q2, right? Splits it in half. But then I have to move through quite a bit of the curve, or 25% of the curve. And then it's going to be quicker to move the next set of the curve. And then it's quicker again, same distance. And then it takes longer. Okay. But we also know 2 standard deviations from the 68, 95, 99.7 rule, right? So here, this area is 50% or 0.5, just by definition of the interquartile range. 2 standard deviations is 95%, the central 95%, just from the 68, 95, 99.7 rule, which has to be something like this. .95. So for a normal distribution, the distance between Q1 and Q3 is less than 2 standard deviations. So here, this is mu minus 2 sigma, and this is mu plus 2 sigma. And that's why that's true. Again, a lot of knowledge going into these true, false. The next one is just a fact. Z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution, right? If we find a large Z-score in either direction, then we know that that's unusual because the area in the tails beyond those points is very, 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 very small. And so that's the probability. And so I'm just going to go for true. That's the only kind of easy one on there. That's a fact. And that's amore. Any questions about those? Yeah. Oh boy. Well, I'm officially behind, but not as behind as the other classes because they have Monday sections, so they're hooped already. So we're still doing good. I'll just adjust the content on the test, but I do want to have some binomial questions, which we'll cover on Tuesday. I know I love the normal distribution and we use it so much. It's worth the time. But I am going to kind of skip 4.2. It introduces some terminology that I'll kind of bring up. But the geometric distribution, I've got read on your own, but how about I just read it to you? Blah, 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 blah. That's just an example. The terminology that I need you to have for when we talk about a binomial distribution, which is different from the normal distribution and how we use it, is we're going to have some set number of trials where we try to get either a success or a failure. And so only two possible outcomes. Okay? And so when a trial only has two possible outcomes, we call it a Bernoulli random variable, but we also need that later on. And so we classify them as success or failure. And there's going to be some fixed probability of success, which we'll denote by P. Okay? And so that's probably all I need you to have. The geometric distribution, I'm not going to test you on. But we need two possible outcomes. Success and failure. This is where you can use the trick of, okay, if you have a success that you're interested in, for example, flipping a coin, then flipping heads is a success, flipping a tails is failure, or that case is obvious, right? Success, failure. What if you roll a die, but you're only interested in rolling a 6? Then rolling a 6 would be the success, and rolling anything but a 6 would be a failure, right? And so as long as there's a fixed probability with a fixed probability of success, and therefore failure if there's only two possible outcomes of success, which we'll denote by lowercase p, in order to use the binomial distribution next week. I'll call it there. I encourage you to read through this geometric distribution example just to kind of develop some ideas. Okay. But we'll leave it there. We'll do the binomial on Tuesday. If you have any questions, let me know. Otherwise, have a great weekend.